my goodness, hello. Turn this down just a smidge a bit. I can do this. Let me see. Hey, notification squad indeed. Tis true, tis true. Alrighty, hello, hello, hello. How is everybody doing today? Everybody's doing absolutely fantabuloso. How we doing, Golmash? How we doing, Jess? Good morning / afternoon. Good evening to you, Golmash. You doing well out there? So, everybody's hopefully doing absolutely fantastic. Good. I'm good. It's a chill Wednesday. That's what we're here to do. Chill and have Wednesday. I don't know there's much more to that than that, but okay. Hopefully today will be another wonderful day. Maybe a little bit rougher on the concept side, but it's okay. You're gonna have a tuna toasty with chicken nuggets. So I'm good. That sounds pretty decent. Sounds pretty decent there, Yosin. Not only am I here, but I'm on time. Heck yes, you are. How you doing, Yosin? How we doing today? Hopefully we're doing fantastic on this wonderful, wonderful Wednesday. We'll have doing some college algebra here. Going over growth and decay today, just to let you know, my dude. Hopefully you're doing well, my man. Trying to pick my first year uni schedule, kind of rough. Well, I will say this, Yosin. Just make sure you don't put in too many credit hours, okay? Make sure you can pick a schedule that you can balance out with your life. You don't want to have too many credit hours, so keep it at a reasonable rate that you can work with. Don't try and overload yourself. All right? It will do more harm than good at the end of the day. But in all honesty, you should always pick classes that are probably you should always pick classes that are your electives first. If you go into regular uni, you should always pick classes that are your electives first, so you can get those out of the way, done and dusted. And maybe pick one class that's related to your major, so at least you're constantly doing at least a class. Again, if you're here in the U.S., then yeah, it would make sense to go that direction. If you're outside of the U.S., then yeah, well, kind of if they make you take superfluous classes, make sure you kind of take care of those and do that one major class, and then once you get it all out of the way, it's all going to be like major classes afterwards. So just depends. So, but I never want people to overload themselves. I've had students that have taken like 15 credit hours, and their brains were shish kebab fried. It was pretty rough to watch. So, what did we learn today? Today we're learning growth and decay using exponential functions. That is what we're doing here today. Growth and decay. And then maybe we'll get into section 5.1, which is a system of linear equations. So, we'll see how far we get with growth and decay here. Honestly, we should be able to get through with it, no problem. But, you never know. Just depends on the pace of the class. Just depends on the pace of the people. So, I may have an agenda, but it depends on everyone else. So, sometimes that agenda is fulfilled. Sometimes that agenda is not. And it is what it is. So, everybody based on the pace of the class, that takes priority first and foremost. So, any plans today, Yosin? I gotta ask you. Any plans for later today? Besides sitting and chilling? Or if this is all we're doing here today? I don't know. I have no idea what that is, Cool Mash. Probably gonna go out play some soccer later. Respect, my man. Excellent. Get a little bit of football in you. Well, soccer in the US, football everywhere else, but you know what? I would understand either way. Because basically, if you want to say, you could say, hey, you could be like American football, and that would be our version of football. But then football is like the world's, like soccer, world sport. So don't be get pressed when I call it soccer. Some people just need to not like worry about it. Yeah, that's fine. Like the way I avoid ambiguity is I'll call football or soccer the same kind of thing. I'll call it soccer/football. And then if I want to be like extra sure, I just say American football. That way it has that distinguishment between the two. So I avoid that way you can avoid people getting, a little chuffed about it. So, just to yeah, there's still a little bit of ambiguity there, but at least it's like okay. Football, American football. All right. So when they hear me say it, they're like, okay, I can distinguish what you're trying to say. Little subtle things like that, they help. Yeah. Stretch this out here. Ugh. Gotta stretch out for a little bit. All right. Yeah. Lysidena, Professor Chibbs, do you have any exciting plans for today? I do have an exciting plan here for today, Lysidena, and that is teaching you. That is my exciting plans for the day, is to help you. Have you been watching the Euros lately? I have. I watched the last minute gasp winner of Ukraine and Sweden. That was a slugfest. That was painful to watch. Like the last hour of watching that match was really painful. Like everybody was absolutely gassed. Everybody was absolutely hurt. There was a lot of hurt players on both sides. Like I don't think you come out of that match without severe injuries. It's really rough to watch. But that last gasp by Ukraine to score the winning goal was amazing. So people talk about the red card that Sweden got. People talk about the red card that Sweden got. That was pretty well deserved. So that was a pretty clear red card. It was the correct decision. I think I was sad when Ukraine scored. I wanted to see Pens. Pens was okay. I think both teams played absolutely fantastic. Both teams played absolutely fantastic. If there had to be a winner, I'm glad it was Ukraine. I will tell this: if you're an English fan, if you're an English fan, England versus Ukraine, this is your way. This is your way to get into this round of 4. This is the way to get to the semis. It's the easy path forward since Ukraine is depleted and hurt. And England has been playing like crazy. Am I an England fan? Well, with my friends in England, I'm going to be an England fan for these Euros. Obviously, I'm live in the U.S., so we have there you go, But yeah, I'm going to be rooting for England for this for these Euros for sure. Khadija, you made it. Hey, good morning/afternoon. Welcome. Lysanrana, any hockey fans? Game 2 for the Cup is tonight. Yes. The Lightning are playing very well. The Lightning barely eked out against the Islanders in this Stanley Cup semis. But the Lightning are always favored. It's like they won last year. The Lightning are a really stacked team, without question. See if Montreal can step up and start playing better than maybe than last game. They got absolutely trounced, so. I want Shea Weber to go down. That's all I care about. Wow. I hate Shea Weber train. You know what sucks? He's a dirty player. There are a lot of dirty players in the league. I remember when the Blackhawks won their 3-cup runs, you know, there was a lot of dirty players you would watch. Brad Marchand, I think it was it Marchand? He was a pretty dirty player. He would always get in someone's grill. Northwest Bruin says, want to become famous? I mean, you're famous right now, Northwest Bruin. You're amazingly famous for being banned. Bye-bye. I can't think about Hawks in the final without thinking about Keith Giddens. Yeah. I can't even think about the Hawks without Jarmelson actually, you know, putting his body on the line for every slap shot from the point. Like, Jarmelson was like the defensive gem. And you had like the first cup run was even more amazing. Oh man. Oh man, Jarmelson always took it for the team. And when we lost him, it was like, oh man, you know, that was a big blow. Because I thought like him and Keith were like the heart and soul of that team. And heart and soul of the defense. And I'm like, oh, I really missed Nicholas Jarmelson, like 100%. That killed me inside when he had to leave because of salary cap reasons. Like I could lose Andrew, I could lose Shaw, I could lose Saad, I could lose, you know, I couldn't fathom the team without Seabrook. But Jarmelson always had a special place in my heart, 100%. Nicholas, hello, good morning / afternoon. How we doing today? How we doing today? All right, ladies and gentlemen. All right, we are here to go ahead and get started here with the newest material. So we're gonna get moving here, and we'll see exactly how things work out, right? So, let's go figure stuff out. Yeah, good stuff. Let's do some intros. Let's get started. Yes. Okay, let's get started today. Welcome back to Wednesday. All right, so we're going to pick up where we left off last time. Last time, we did exponential equations, lots of examples with that. We did log equations, lots of examples with that. But there's just a ton of examples here last time about using our log properties, exponential properties, a lot of different looks here about how to focus on that here. Now today, we're going to finish off chapter 4 here with the last section dealing with exponentials. Again, in this particular section, we're going to be dealing with word problems. Yeah, I know everybody loves word problems. And more importantly, we'll be dealing with growth and decay and modeling data. So that is the plan here for today, is doing stuff here with growth and decay. So let's go to the big board here. Go ahead and take a gander at what we're going to be looking at here. And yeah, let's go ahead and do some problems. I think that sounds like a plan. Okay, so we're going to start here at question number 3 from the handout. And we're just going to go through a few of these questions here. Actually, let me make this a bit bigger so it's on a single page. There we go. Zoom out. There we go. Oh. Please, thank you. All right. So let's look at number 3 and number 4. So number 3 says, what is the formula for exponential growth and decay? So what we have here is we have a formula that we're going to use, which is a is equal to a0 e to the kt power. Okay, so that's what we have here in this instance. Now, What is A is equal to A is 0 to EKT power? What does each of these letters represent? Well, first and foremost here, we have A0 being the initial amount. Okay, so when we use like growth and decay, for example, typical application problems for growth and decay would be like for say, hey, I have a number of bacteria in a petri dish. Well, how many bacteria are going to be in the petri dish after X amount of time? Okay, or I have X amount of a mineral in the ground. How long is it going to take to degrade to X amount? How many years is it going to take, for example? So oftentimes, if you talk about, say, practical applications would be like biodegradability. All right, so how fast does something biodegrade over time? All right, and if you're talking like environmental impact, that's especially important. Okay, so certain things have a very fast half-life. For example, we'll talk about that. Not the game, mind you. And then other things have very slow half-life. All right. In any case, we have to start off with an initial amount here. So we have A0 is equal to the initial amount. A is the ending amount. That should say amount, not among us. It should say amount. I can actually spell. Spelling was not one of my things. Even though I taught English for 4 years, spelling was never my dealio. I don't know why, but you're just gonna have to run with it. So, all right. I'm just gonna switch that up here, make it a bit. All right, there we go. All right. Okay, so A0, the initial amount, A is the ending amount, K is going to be the constant of growth / decay. That's going to be a constant. So again, you could talk about it as like the percent at the rate that it's growing or decaying. And T is time, and time is going to be dependent on context. If we talk about minerals of the ground, it could be years, months, whatever. Okay, if it's bacteria, it could be minutes, seconds. Okay, it could literally be any of those things. So it depends on the context there. All right, next, if k is bigger than 0, then essentially the constant here, the way we define growth and decay is very simple. If the constant of a growth and decay is bigger than 0, then that's going to indicate growth. You're growing, okay? If you have k is less than 0, then that is indicative of decaying. All right, so that's essentially what we have there for that. Man, how many mistakes did I make here? All right, that again. All right. So we're going to look at examples where we're going to directly use that there and see what we actually end up with, right? So hopefully it should not be too hard. It should be pretty easy and yeah, not too shabby crabby. We'll also look at another application here, which you can see that I'm kind of making bigger here on the bottom, which is talking about logistic growth models. So this is A is equal to C over 1 plus A e to the negative bt power. Now, where is this actually useful for? This is actually used for, say, population growth. Talking population growth, you can use logistical growth models. So, for example, how fast is a city growing? Okay, from, say, projections year over year, you can model that data. You can actually see how, what the predicted value of what the population should be in, say, the next 5 to 10 years or whatever. Maybe next year you have an expectation, whatever the case may be. Now, that's all well and good. We'll talk about modeling data here. That'll be the last question here when we look at some examples. All right. Let us go ahead and do some examples right now. All right, let's do it. All right, so I'm going to write down a couple of these word problems here. All right, I'm going to go ahead and do it. Okay. All right, so let's start off with something easy, and then we'll work our way up from there. All right. Okay. I wanted to. There we go. I got it. All right. So, example: an artifact originally had 16 grams of carbon-14 present. Decay model, and I'll be posting this decay model here. We have a very specific one here. So we're just going to see here. So 0.000121T. This is our decay model here in this instance. Again, K here is a negative, hence why it is a decay model. Okay. Describes the amount of carbon-14 present after T years. All right, let's answer a couple of questions in relation to this example. Yeah, I'll put this on the next page because there's not a lot of space. Okay, so first question here. After how many years, actually not after how many years, how many grams, God, I'm getting this backwards here. How many grams of carbon-14 will be present after 571 years? Actually, let's go 5,007. And then after 11,004. All right. So this is going to be our question that we want to go ahead and answer here in this instance, okay? All right. Okay, so in this particular case, we're given this model here, and we want to go ahead and solve for it in both of these instances. So let's do it out. Again, it says how many grams of carbon-14 will be present after 5,715 years. So all we're going to do here is we're going to place 5715 in for T. So we're going to have negative 0.000121 times 5715. Okay. Now, we have the full expectation to put this in the calculator appropriately. Okay, so again, let's go ahead and figure that out here. This will give you a good reminder about how we entered in E in our calculator here from last time. So bust out the calculator here. Go ahead and do this together. Okay. All right. So what we're going to do here is we're going to go ahead and put 16. And again, to get the E to show up on your calculator here specifically, we're going to go ahead and hit the second key and hit the LN key to get E to show up on your calculator here. And then we'll go ahead and put negative 0.000121 times, and then 5715 here. And we'll close those parentheses just like so. Then hit enter. Okay. We take a look here that we get 8.013. All right. 0131 if we go 4 decimal places. All right. So this is how many grams are left after 5,715 years. All right. Are there any questions about that? Hopefully that's not too bad. Nope. All right. Alrighty. Okay, so the next thing that we're going to do here is let's answer question B. Question B says, how much is left after 11,430 years? No, and I'm back. All right, welcome back. So let's do 11,430 years. So we have 16e to the minus 0.000121 times 11,430. Okay, go ahead and put that in the calculator. So we put 16 second and natural log. Negative 0.000121 times 11,430. And we get 4.0131. All right, fine. Okay. Any questions about that so far? I hope that was pretty straightforward. I hope so. All right. So far, so bueno. Okay. Now, these are pretty simple because all we gotta do is just plug in the values here. But what if we had to go backwards, for example? Well, that's a little bit of a different story. Okay, let's answer a couple of more questions here. Again, so carbon, for example, this is actually a rather important problem in actual practical real life application. You ever wondered how you can figure out how old something is? What they do is what they call carbon dating on that particular item. And in order to do carbon dating, you actually take this exact model here and you can approximate exactly how old an object is, whether that be a physical artifact, whether it be an artifact or a rock or whatever the case may be. If you can measure how much of carbon is left in that particular piece, you can actually accurately see how old that particular piece actually is. So if you're ever wondering, how do you know something is like, 10,000 years old, well, there is a mathematical way to go ahead and find that. Okay, so let's look at the next question here. I'm going to go ahead and type out the next example here, which will use this same thing that we have up here, but in a different context, just a different way. So let's say we have a prehistoric cave painting was found in France. All right. The paint contained 15% of its original carbon-14. Estimate the age of the painting. Okay. So let's go with this here. So the prehistoric cave painting was found in France. The paint contained 15% of its original carbon-14. All right. Estimate the age of the painting. All right. So in order for us to go ahead and figure this out, we're going to take a look at, again, we're going to use the same model that we have here, this e to the negative 0.0021. Now, the model that we'll use here specifically, just for this particular example, be the generic model here. So a is equal to a0, and then we'll have e to the minus 0.000121 times t. So this will be our model that we'll use generically for this particular process. Now, let's talk about something here that you do not see. What we don't see here is we don't know exactly how much the initial amount is going to be. We don't know that, okay? That again, all we know is that there was some amount of carbon-14 in this painting, a random amount, and that somehow, some way, we had 15% left after X amount of years after it was rediscovered. Fine. Okay, so how do we go ahead and put that into a problem that we can actually solve if we don't know the initial amount? Well, in this instance, we're going to go ahead and make an assumption. All right. Now, that assumption here is you could do it one of two ways. And so let's talk about the trick here. There's two numbers you can assume. The trick is to assume that A0, I should say the initial amount, A0, is equal to 1 or 100. Either way, you can pick 1 or you can pick 100. Either way, you should arrive at the same result. Okay, we're just going to make that assumption here. All right. Now you're probably wondering, why am I going to assume it's either 1 or 100, no matter which way I choose? Well, it's because we're given a particular certain percentage amount that is left over. Now I'll let you guys decide here. Should I choose, you guys pick. Pick a 1 or 100 that you want me to start with. Which one is going to be easier for you to see? I don't know. That's why I'm going to ask. 100? Okay. We'll pick 100 if it's easier for you to see 100. That's fine. I don't mind. All right, so let's assume that this is 100. This is like 1. Well, I'll show you how you can get 1 or 100 either way. Now, if I assume that it was 100 and 15% was left, how much should I have at the end of the day? If 15% was left, how much is left over? Not left over. How much is left? I have 15% left. Not 85%. That's how much is lost. How much is left? Elias, I don't know. The answer here from Nicholas is 15. So if we started at 100 grams and 15% was left, then we have 15 grams left over. If I chose 1, yeah, so again, you just have to be able to see that there. Again, if I chose 1, I would have 0.15 there on the left-hand side. No, that's okay. Yeah, it happens. No worries, no worries. Just making sure we get that cleared up. Okay, so what we're going to do next here is, if we're going to solve for t, we're going to go ahead and divide by 100 first. Okay, first things first. Just going to divide by 100. The left-hand side, we're going to get 0.15. And again, you would get 0.15 if you chose 1 on the left-hand side. Either way, you get there. All right. Okay, so we have 0.15 is equal to e to the negative 0.000121t. We got to solve for t here. All right. So, can you guys tell me, what should I do next? How am I going to be able to solve for t? That's what we got to be able to find. But what do I do here first? How can I solve for t here in this instance? How should I solve for t here? Joe said, would you use the power rule? I would, but I have to do something before I can do the power rule. So I like your train of thought there, Josie. I like your train of thought. That's a good. That's definitely good to say, but you got to do something before you can apply. Natural log where? All right, we're getting there. Natural log where? All you said is natural log. I said natural log. Where are you going to put natural log? Both sides. Okay. Very good. So both answers here are correct. You're going to take the natural log. You have to take the natural log of both sides. You guys are going to fill in the gaps for me here. I'm going to take the natural log of both sides. That's what has to happen here. Okay. On the left-hand side, I get natural log of 0.15 equals, and again, the natural log and e will cancel out. That leaves you with negative 0.000121t. All right. Are there any questions up to this point? I hope that made that clear at the very least. Any questions up to that point? I want to be sure everybody's got that part down again. Just like what we did yesterday, doing it again today. No thanks. No thanks. No. Yeah. Okay. All right. Okay. So next, we're gonna go ahead and divide by this long decimal. And again, plug it into the calculator here for sure. All right, so let's go ahead and look at that on a calculator here. So remember, if you're going to do natural log of 0.15, remember to close those parentheses first, and then divide by negative 0.0001. Oh, I don't need that. I don't. And so here we have the painting here is the T is 15. Do we need to round? Let me see if we round to the nearest year. Yeah, okay, so round here we have 15,678.7. Or again, if they want you to round to like the nearest year, then this would be 15,679. Okay. Alright, and there we go. We got our final answer for that problem. Bueno. Alright, let's take a look here. Use a real life here. Oh, okay. Well, that isn't too bad. Okay. Alright, so alright, let's do the next one then. Do another example. For example, let's do more. Alright. Alright, so let's do the let's do half-life here. So the half-life of lead is 22 years. Alright. How long will it take for a sample of this substance to decay to 80% of its original amount? Okay. So let's look at this one here. Now, what I need to talk about here in this particular question is talk about the concept of half-life here. All right? What exactly is half-life? Okay, in terms of its actual definition. Half-life here, its actual formal definition here, is basically the amount of time it takes for a substance to decay to half of its original mass. So most things take, years to go ahead and decay down to half of its original mass. So meaning to say, let's say you started off with like 10 pounds, how long does it take for that particular substance to go from 10 pounds down to 5 pounds? Okay, that would be indicative of half-life there in that particular circumstance. So in this particular case, we talk about the half-life of lead being 22 years. And we want to say, okay, well, if it's 22 years, having a PTSD of geology last semester. Sorry about that, bro. I promise you this is the far as we're going to go in this particular topic. I'm not going to ask you about igneous rocks, okay? All right? And particular stratum, all right? And things that you can find in the Cambrian era of Earth's evolution, all right? Or Pangea. Yeah, we could talk about Pangea. Let's talk about Pangea and the tectonic plates. All right, let's talk all about that. All right. There you go. I'm not kidding. Fair enough. All right. Let's move forward then. Okay, so what we need to do here for this particular example is we have a couple things that we need to figure out. First of all, we don't have an actual model here. We don't know the rate of decay here. We do know the half-life of this particular thing. It happens to be 22 years, but we don't actually have a rate of decay in this particular problem. So in this instance, how do we go ahead and find that constant k and then be able to solve this particular problem? In a sense, you're going to be doing this problem 2 times. Again, half-life, this with the formal definition here being half of its original amount, all you need to do is just go ahead and say, okay, if I start off with, say, 100 grams of the substance, let's just go with 100 here, do the same assumption of 100 or 10 or 1 or whatever you want. You're just going to say, okay, let's say my initial amount is 10. I'm just going to assume that. Say the initial amount equals 10. So I have 10 e to the k, as I don't know how fast it's decaying, but I do know how much time it'll take. It'll take 22 years to get half of my original lead. So half of 10 is going to be 5. Okay. Now, all I have to do is just go through the problem here and solve for k. That's the first half of this. So we'll divide by 10. So we're going to get 1/2 here is equal to e to the 22k. We'll go ahead and take the natural log of both sides, just like we did the last problem. And the natural log and e will cancel out. So we have natural log of 1/2 equals 22k. And we divide by 22. All right, so we totally enter this into our calculator here. All right, let's enter this in. Now, I will point this out here. be sure to put in the, this is our answer here for K. But be sure to put the decimal points here. Again, if it asks, on certain problems on my math lab, especially for the homework here for like these type of problems, it may ask for like 6 decimal places or something akin to that. So it's going to ask you for a lot of decimal places here. Please be sure you put in those like 6 decimal places, okay? You want to use as exact of an answer as you can in order to get the correct answer for the problem. So in this case, I'm just going to write K all the way out here. So I'm not really specified with the number of decimal places. So 0.03150669. The rule of thumb in mathematics is you don't round until the end of the problem. You don't round in the middle of the process unless it's asked. So okay, so now we have K. All right. So before we move forward here, are there any questions? Stretch these arms out. One question? Go ahead, my friend. Absolutely. Please ask as many questions as you need, okay? Feel free to interrupt me if you need to, okay? If I'm going too fast, just let me know and not a problem. Why does the natural log cancel on the right side, remains on the left? Okay, so that's a property of natural log, okay? So the property of natural log here is, again, natural log of e to the x is equal to x. This is one of the properties of natural log. So in effect, what you can see here, George, is that you can effectively, a crude way to look at this is like canceling out the natural log in e. So I'm using a property of natural log that we've talked about here a couple of sections ago. In order to justify that. I can't do much with natural log of 1/2, but I can do stuff with natural log in e in order to get that 22k to basically come out. Can we see the original formula again? The original formula for yeah, okay, I know what you're talking. Here you go. Sorry about that, Jess. All right, took me a second to think about what you. Joseph says hydrate. Okay. Thank you for the hydrate, Josie. Get me my coffee in me. All right. Any other George? Does that answer your question there? Let me know if you have any more questions there, my friend. No problem. Okay, cool. Any other questions before we move forward? Any other questions? We're not done with the problem just yet, by the way. We're halfway there. But I will say that this is the hard part of the problem, is just to get to this k. Once you got this k value here, the rest of it's actually not as bad as it may seem. Okay. All right. So the next thing that we're going to do here is we want to go ahead and see, let's take a look at our problem here. We want to say how long will this take the sample to decay to 80% of its original amount. So if we talk about 80%, we know how fast it's decaying, and we're going to use this K we just found here in order to find out how much time it will take to get to 80% of its original amount. Now, in order for us to test that out, again, we can use the initial amount here of 10 that we used at the very outset. So let's write down the problem here again. We have 10. The only thing here is that we have 80% of its original amount. So 80% of 10 is going to be 8. That's reflective of this 80%. Okay. So I just took my assumed original amount of 10. And like I said, you could literally use any value here for your initial amount, 1 or 100 or 10. Okay, again, you just make the adjustment here based on the percentage. And the difference here is you have e to the negative 0.03150669. And again, in this instance here, all we're doing here specifically is we're going ahead and doing the same thing. Oh, this should be the t power. We're going to go ahead and do the same thing that we just did here before, only we're just now solving for t as opposed to solving for k. So, and we just start off doing the same things here from before. Divide by 10. Nothing different here. All right, so here we get 0.8 is equal to e to the negative 0.03150669 t. I'm going to go ahead and take the natural log of both sides. And the natural log and the e will cancel out. So you have natural log of 0.8 is equal to negative 0.0315669t. And then we'll divide by that amount on both sides to see what we get for t. 150, I forgot the 0 here. 50669. Almost forgot that. All right, and we'll go ahead and plug that into the calculator. See what we get. So natural log of 0.8 divided by negative 0.03150,669. And let's go ahead and see what we get. So here we get 7.082. All right. So it's gonna, for it to get down to that, it'll take 7.0824 years to get down to 80% of its original value. And that's it. That's all you gotta do for that. Essentially, like I said, doing this process twice here, first solving for k, and then going ahead and then solving for t based on the premise it actually asked you. Okay. Any questions about that? Any questions? Okay. No. Hey, Michaela. Real viewers, yes. I can't post a link here, but I'm glad you were able to come into my math stream, Michaela. Appreciate that. All right. Okay, so let's go ahead and focus on the next part here. All right, so the next thing that we talked about here is going to be, let me scroll back up here for a moment. We talk about logistic growth models, okay? So we could talk about that here as well. We can model, again, if we want to model, for example, here, how many people will be on Earth after an X amount of time. All right, we can certainly discuss that here as well. Okay, so let's go ahead and taking a look at this. There's actually a pretty decent question here. Where is that? There it is. Okay, so they do give us a function here for population growth here on Earth. That's a little bit different these days, but you know what? Okay, so let's say this is the population function here for this particular example. This will be part of our example here. So let's say this is a logistical growth model for the population of the planet. Okay. All right, so we have a few questions that it asks us here. Okay, and just go ahead and see. Okay, and then we're given here context here. Sorry, I should give context. X here is going to represent the number of years after 1949. Okay, so X is the number of years after 1949. So just a little bit more context here about what X will represent. Okay, so let's answer a couple of questions here. It says, when will the world population reach 8 billion? Okay. When will the world population reach 8 billion people? Okay. So in order for us to actually see the world population here reach 8 billion, let's go ahead and write it out. Okay. So we're going to take this logistical growth model, and we're going to go ahead and set 8, which is 8 in 8 billion, equal to this guy right here. So that's essentially what we're going to do. So for our example here, we're going to set 8 is equal to 12.57 over 1 plus 4.11 e to the negative 0.026 to the x power. Okay. And again, we want to go ahead and solve for x here. So how do we solve for x here? Let's go ahead and talk about how to do that here. Again, what we want to do first is we want to go ahead and multiply by this big old expression. I don't like stuff in the denominator, so it's like, well, I want to kind of get rid of it. Let's multiply 8 by this whole thing. Alright, so here we're going to get 8 plus, and then we're going to just do 8 plus, second here. You can do that on the calculator. 8 times 4.11. So 32.88 e to the minus 0.026x equals 12.57. Alright. Again, the way I got the left-hand side here, by the way, just to let you know, is I distributed the 8 to both of these terms here. Okay, when I multiplied on both sides, alright? So Just letting you know where I got the 8 and 32.88 from. I distributed 8 to the 1 and the 8 to the 4.11. I multiplied them and got this, okay? Okay, so what I want to do next here is to go ahead and we're going to solve for t here, or x I should say. Let's go ahead and subtract by 8 on both sides. First, get 32.88 e to the minus 0.026. X equals 4.57. And then we go ahead and next we go ahead and divide by 32.88. So let's go ahead and see what we get there. We're going to get a pretty funky decimal, I'm sure. Alright, so this is what we have here. Now this is some random decimal. But can I scroll back up these? Yes. Again. There you go. Alright, here I can go ahead and take the natural log of both sides. So I'm going to get minus 0.026. X equals natural log of this guy. And then we'll divide by negative 0.026. Okay, and then we just plug that into the calculator. Let's see what we get. Get natural log of 4.57 divided by 32.88. That's going to be some random value. I don't really care what this value is, because I'm just going to take that answer, divide it by negative 0.026. And so here I get x is equal to 75.89. So 75.9, or approximately 76 years. So 76 years after 1949, since that's what x represents. So let's see here, 76 years after 1949. Let's do that part there. So 1949 plus 76. That's going to be 2023. Okay. So it'll be by 2023 that the world population here, according to this logistical growth model, will be up to 8 billion people. All right? And there you go. Okay. Any questions about that? Hopefully that was pretty straightforward. Wait, what did I get that wrong? Oh, I thought, oh. Yeah, you're right. Whoops. You're correct. Just a smidge. You're correct. Very good. Thank you, Josie. There you go. zoom out a bit. You got me, thank you. This is actually pretty important if you're talking about world population. World population is definitely one of those things that you have to think about. Remember, at the end of the day, no matter how big people say Earth is like this really big and vast place, regardless of what people think, Earth is still a finite resource, so you can only fit so many people on planet Earth and sustain its population. After that point, you get into natural selection where basically based on biology, that the population of a particular area that can sustain a particular population of whatever that may be is going to fluctuate up and down. It'll reach a maximum point based on the resources that are available in that particular area, or in our case, the entire planet. So, also, I would have to say, in terms of like population growth is something that does affect you as well. Things have changed a lot in the past, like, say, 30 years, I would say. If this was real, it'd be just 4 years away. I mean, we could look at the world population approximately right now. So it's not that far off. Let me be honest with you. World population here in 2019 was 7.6 billion. It's not the worst model that you can come up with to say that it's going to be, 4 years away. I mean, we may be a little bit past that. Remember, it's a model. It'll give a it's a predictive model. So whether you reach that 8 billion a touch before or a touch after, it still shows a reliability based on what that model is. So when we talk about modeling data, again, we want to get a good ballpark estimate to give ourselves a prediction about when this could happen. Right around that ballpark estimate. It's like if we talk about world population of countries, the population growth rate is slowing in some countries the population growth rate is going down as opposed to going up. So like in Japan, there's a lot of people who are older, who will in the next generation will be slowly dying away, and then the population of Japan will actually slowly decay over time. So estimates put that the country being like 110, 120 million, going down to possibly 80 million by the time 2050 runs around. So, which is certainly a real possibility. So, birth rates have a lot to do with it. Society has a lot to do with it. There's a lot of general trends that you can judge just based on modeling and why things are happening the way they are. So it's fairly interesting. You can see even the world projection by 2025, they expect it to be a touch above 8 billion. So it's fairly interesting because children are seen today, like having kids. Having kids is very different in today's society. Working with a lot of COVID babies, yeah, there are a lot of COVID babies. And that's great. I'm glad that you're having the population go up. It's just how people actually view having children today. I saw it like when I was living in Japan. I could see the trend, trends that were happening in Japan when I was there over 10 years ago are happening here in the United States, which are really, really different. At least how people view having children. It's a very, very interesting. So like, a good example is that a lot of people are recognizing that they're spending more time at work, and just trying to get a living wage. And because they're just spending time having a living wage, for some people, marriage isn't even an option on the table. Having kids isn't even an option on the table because they feel that if I can barely support myself, I can barely support a child. So a lot of people opt out of not having a child instead of or not even getting married in some cases until they're very late, or they decided not even to go ahead and do so. And of course, that's going to lower the birth rate as a result. So And and that happened in Japan like 10 years ago. Like women before, if you go back to Japanese history, because it's fascinating what's happening in America. It's like almost a carbon copy of what I saw back there. Like back in the 30s and 40s, when World War II, before even that, women didn't have a lot of rights in Japan. Women had like it was arranged marriages, the whole 9 yards. There's still arranged marriages in Japan. They still exist, but pretty much you got married as a teenager to some young guy, and then that was pretty much it. That is that is not seen in pretty much most cases around Japan. Some cases I did see it, but very rarely these days. In the 80s, women still didn't have a lot of leeway, at least up until the 1980s when Japan started to be more, started to be a economic powerhouse. And women got a lot more freedom to do what they want, like even leave the country and that sort of deal. That still wasn't underneath law until the early 80s or beginning of the 80s. So what they called it, they had like their sexual revolution during the 1980s, and women were able to do what they want and do what they pleased, right? But you know, it was at that point that the mid 1980s came around and their economy went bust. Okay, not so much bust, but they kind of went stagnant. And most of the time, most people at that point were working. More women were working. In the more women were working. Some women became housewives, whatever the case may be. There was still arranged marriages, but over time, women had been working and working and working in the workforce, and they did exactly what I kind of described. They're like, you know what? I'm working so much. I'm hanging out with my colleagues. That's my social life. And they're like, well, I don't have time to have kids if I'm working overtime. If I'm getting home at like 11 o'clock at night and I'm waking up at 5 in the morning or something like that. I don't got time to get married. I don't got time to have kids. I don't got time to have a husband. If the local government is actually literally giving them money to have kids, it's rather remarkable that they still, again, they don't want it. They don't have the time to do it. And so you saw the shift go from getting married when you're like a teenager, and that shift went early in the 80s, like in your early 20s, and now it's like in your early 30s, mid 30s is when some women decide to get married or not even opt in at all. So it's a fascinating trend to see, and a lot of it has to do with the work culture. And I see the same thing that happens here in the United States, is that the work culture has pretty much is almost like a carbon copy from what I saw back then, and attitudes toward marriage on both sides. Um, I use women because that was kind of like the biggest change gender wise, but I see it on both sides where it's like it's not worth the effort anymore. So not worth the effort. It's not worth the time. So lower birth rates as a result, and yeah, developing nations will have lower birth rates as a result. So the plant and pet business is booming. That's true. I want a pet. My child is a cactus. I give it a little bit of water. It kind of stings, but it's a love sting, right? It stings. It stings me in the. It stings me. It's like boop. Ah. A lot less of a financial burden. It's a big decision to have a kid. It's a big decision. Children are different. Children are viewed differently today by modern society than they were back 100 years ago. Back 100 years ago, children were a commodity. Now that's not the case. Okay, now children are no longer viewed as a commodity. The reason why I say children were viewed as a commodity is because modern medicine hadn't really made the forefront by that point. There, the life expectancy wasn't as high because modern medicine hadn't made those breakthroughs yet. And so when you had modern medicine make those breakthroughs, then children, more kids, would last through their younger years, and you no longer had to view children as having kids constantly in order to maintain a family or maintain a farm, or whatever the case may be. So having fewer kids was certainly you went from like having 5 kids because you're hoping that a few of them would survive, to now you can have 2 kids and have the peace of mind that they're going to survive. So um, forget them kids. Link's like, forget them. Puh, you're done, son. Like, okay. My family has been trying to guilt trip me into adopting a pet for the past week, sending me photos of pets up for adoption in our group chat. Wait, why? Why is why is your family trying to guilt trip you? I don't understand why they're trying to guilt trip you specifically. Survival of the fittest for mottos for kids back in the day. That's true, Jess. Because my boyfriend and I have a house, and naturally we need a pet. I mean, it's a decision between you and your boyfriend, nobody else. It's your house, so then tell them to deal with it. It's a house that you and your boyfriend share. It's a mutual decision. You just tell them to keep out of it. You're like, hey, I love you guys, but hey, we're not ready yet. We'll get a pet when we're ready. Fine, done. Yeah, that's just how it is. Okay, then that's fine. Get a pet rock. I mean, I don't want to get any more pets because I like being able to stay out with people until like 4 a.m. Ah, it's so nice to be younger. I respect that though. Pets are definitely family. Travel without needing a sitter. Get a plant, just add decor. Actually, Jess, why don't you do one better? Get a plastic plant. Then you don't even need to do anything. And there you go. Get a plastic plant. Everything I touch dies in regards to plants. Well, if everything you touch dies when it comes to plants, like Serena, then the same thing is true when it comes to cooking for me. Everything I touch burns when it comes to cooking. So I definitely must say again, forget them kids. As a mother, I chuckle at this. Josie, how many kids you got? I have to agree with Blink. I can help you. I got a green thumb. Hey, there you go. 3 bad kids. Wait, 3 bad kids? Hold up a second. 3 bad kids? Well, I like how you characterize right away. 3 bad kids. Wait, why 3 bad kids? It's very descriptive. Everything I plant becomes invasive. I got some kudzu I can give you, Jess. Kids are great when I can give them back to someone. You're like, I love visiting my nieces and nephews, but here you go, take them back. Love you guys, but what? They're right back to you. Oh goodness. As you can see here on the screen, you can see there the birth rates of certain countries. Like Japan and South Korea have the lowest birth rates in the world. Italy, Germany, Spain, Poland, Canada. We're actually right up there. United States is actually underneath the replacement birth rate. Um, so replacement birth rate is like over 2, and then clearly we are under 2. So there you go. So 43.7 annual births per 1,000 years. So again, in Japan, you have 7.7 births for every 1,000 people. In the United States, you have 12.5 births per every 1,000 people. Um, so yeah, it's pretty low. Twenty hastas in Ah. Holy, check out the lowest. Yeah, look at that. Japan and South Korea, the 2 lowest birth rates in the entire world, and for major countries. Fairly interesting that you can actually view that here with modeling and what. Except them bunnies keep eating them. Isn't that a good thing? If the bunnies keep eating them, isn't that good because they control the plants from spreading and being invasive? Like I kind of look at it that way, you know. Yeah, but I thought that you were going to go get that replaced once the storm blew through. You know, I thought you were going to get that ugly ass siding replaced. I believe wasn't that the goal? Wasn't that the point? I believe? Question mark. We didn't get any damage. Womp womp. Womp womp. Want to scare the buddies? Get some fox fur and spread it around. Oh, I didn't know that was a thing. Hey, Brianna, how are you? Good to see you, Brianna. It's all about the ugly ass sighting. Oh no. Oh no. Oh well. I'm doing good, Brianna. I told him we had to burn the house down and start again because it was that bad. Apparently, that ugly ass sighting has been really getting to you that you want to burn the house down. Accidents happen like that. Don't. It was an accident. You know, I understand that you obviously didn't want to kill a fellow creature. That's understandable. It happens. Okay, you're only human. I can't wait for summer class to be over. Let's take a poll here, ladies and gentlemen. Let's take a poll. Let's do a poll. We'll do a poll here. All right. We'll take a short poll here. I'll have you guys decide here. I put up a poll there. Say end class and start chapter 5 tomorrow. I will be posting up a chapter 4 test either today or tomorrow, okay, or possibly over the weekend, because chapter 4 here is effectively done. So again, chapter 4, it's going to be its own test, by the way. So I'm just going to let you know about that right now. All right. So what do you want me to tell you, Blink? You knew there was going to be a test on chapter 4. It was written in the syllabus. What else am I allowed to say? I'm not finished chapter 3. Hey, I understand. I understand you're taking it at your own pace. You're taking it at your own pace. Do we have class on Monday? What's on Monday? What's Monday? Am I forgetting something? Oh, right. Actually, that's a good point, Nicholas. You know what? I'm going to check on that actually. I'm actually not sure. Um that's a very good question. Let me check the academic calendar for us. Um and then I'm gonna see if that's the case or not. So let me take a look and see if that happens to be the case. So um honestly I always get confused about it, so I do apologize if I'm like super confused sometimes about scheduling and whatnot. So let me check. Spring. Okay, so that's spring up to spring 2021. So I need the next year one. Hang on a second. All right, everybody says yes. So give me just a second though. I want to actually answer this. Is a very good question, Nicholas. So let me answer your question there first. So here is that. So we are okay. We are off on Monday. Okay, so thank you for letting me know there, Nicholas. Never know sometimes. So yes, we are off on Monday. Okay, so uh, just to let you know here, we are off on Monday here, so I will not be broadcasting a class here on Monday. All right, just because the reason why I think that why I thought we might have had class is because the 4th falls on a Sunday. So I'm like, okay, well, if it falls on a Sunday, we still have class or something like that. So I usually just kind of go off of whenever the holidays actually fall. But yeah, if that's what they say, then that's what I'm going to roll with. So that shouldn't be too much of a problem, though. Even if we do miss one class day, we're still on pace to finish up the course without too much trouble. So that is what's on the agenda there, moving forward. You have another math question? Go ahead. Next year, I either have to take finite math or discrete math. Do you know the differences? Which one is easier in your opinion? I would have to say, I said I'm posting practice test today or tomorrow. So Brian, if I post a test, then I always post the practice test to go along with that. So I will post the practice test and the actual test. That is, yeah, but that'll be either today or tomorrow. Yes, that's correct, Brian. For chapter 4 only, by the way. Chapter 4 only. All right. To answer your question there, Nicholas, discrete math is a little bit more proof heavy. Finite math is a little bit less proof heavy. You don't really you do modeling and whatnot, but you do like kind of a smattering of a lot of different things in finite math. So yeah. So the 32.88 here, Fritz, came from 8 times 4.11. That's where the 32.88 came from. So when we multiplied by 1 plus 4.11, all that stuff on the other side there, Fritz, we distributed the 8 to both terms. Yeah, so if I were to pick something that probably be more up your alley there, Nicholas, I'd probably pick finite math. Uh, uh, it depends how you think, Nicholas. But if I were you, then I'd probably pick finite math. That may be the easier of the two options. So again, it just depends on kind of how you operate. But if you're more of like, hey, I need to visually see things, I need to be able to see numbers and stuff like that, finite math may be more up your alley. Discrete math is a little bit more abstract. So maybe you're not too comfortable with that concept. I'd be like, okay, fine. Not too good with the abstraction. Maybe I need to see something more concrete. Maybe that's the way to go. Otherwise, if you see things the other way, if that satisfies, how you view things, then go with discrete. So I would say finite if you're more into the numerical side of things. You get a lot of different smattering of things in finite. So all right, cool. Any other questions you guys have? Any other questions? All right. No more questions? Alrighty. Well, that's perfectly fine if there are no more questions here. Switch to my face cam. Okay. So to serve as a reminder here, we're going to do a couple sections here tomorrow. Okay, so we're going to come back here. Same time, same place here tomorrow here at noontime. We're going to start Chapter 5. We're going to do a couple sections there. Now, just to give you a little bit of a heads up here for tomorrow, we're going to be doing Section 5.1, the start of Chapter 5, and then we'll be skipping 2 sections of Chapter 5. Sections 5.2 and 5.3 will not be done, and we'll be going right to 5.4. Okay, so again, any sections I do not cover here in this course will never be reflected on the exams, okay? So only the sections that I do will ever be on the exams here, all right? So we're not doing sections 5.2 and 5.3. Those are out, okay? So just to let you know, you will not see curveballs. You will not see questions from those sections. That will not happen, okay? So section 5.1 and 5.4 is what we are going to be doing here tomorrow, all right? Good shit. All right, so I want to thank you, everybody. All right, thank you very much, everybody, for coming on out here to the stream once again. Thank you so very much. I love you all. All right, we'll be back here tomorrow, same time, same place. And as always here, everybody, stay safe, stay healthy. But, of course, as always, and most importantly, stay sane, everybody. All right, have yourself a very wonderful afternoon/evening, and I'll see you all tomorrow. Take care of yourselves, everybody. Have a great one. All right. Bye. Bye, everybody.